Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to go through an example of using the Biot Savart law to calculate a magnetic field due to some current configuration. So in this example, imagine we have a wire that stretches a long way to the right, and we have a current in that wire that's to the left. That wire then is bent into a semicircle here, and then it's straight, leaves vertically. So in this area, the current is to the left. Then we have this current along the semicircle path, and then we have a current up. And what we're going to do is we're going to try to find the magnetic field or some sort of expression for the magnetic field here at this point, which is intended to be right at the center of this circle. So what we're going to do is we're going to use the Biot Savart law. We're going to write that out. dB is equal to mu sub I over 4 pi ds cross r hat over r squared. And we're going to apply that law at these different points in this current. So first of all, let's talk about this segment. Actually, before we do anything, we should put a coordinate system in this because we're dealing with vectors. So I'm going to go ahead and put a coordinate system right here. X, Y, now, to deal with this wire segment, what I'm going to do is break this into chunks. So you imagine a piece of it of length ds. The ds vector would point this way. Now, in this example, the magnitude of ds would be the same as dx. And because it points left, that's in the minus x direction, so I'm going to put minus I for my direction. Now, the r hat vector would point this way as well, because remember, r hat points from here to the point we're interested in. If we try to use the Biot Savart law, we're going to have mu sub I over 4 pi ds cross r hat. Now, when we do the ds cross r hat, we're going to get magnitude of ds, magnitude of r hat, sine of the angle between them, but the angle between them is 0, and the sine of 0 is 1. So the magnetic field contribution here due to this wire is 0. Let's do the vertical piece while we're at it. ds, if I break this into little pieces, little elements, ds always points in the direction of the current. It's going to equal dy in magnitude, and it's in the plus j direction. R hat points at the beginning of ds, and it points to the point P you're interested in. Now you'll notice that the angle between them is pi, or 180. So when we do the ds cross r hat, we're going to have magnitude of ds, which is dy, magnitude of r hat, which is 1, times the sine of 180 degrees, but the sine of 180 also 0. So there's no magnetic field contribution to the vertical piece either. So we only need to worry about this quarter circle piece. So now I'm going to take a look at that quarter circle. I'm going to come up here and look at a little ds vector. I can do it anywhere along here. I'm going to go ahead and do it right here. There's my ds. My r hat would point this way towards P. The magnetic field contribution, dB, at this point, due to this current element, remember the current is this way in the direction of ds, this is going to equal mu sub I over 4 pi. Now I'm going to do the ds cross r hat. That's going to be magnitude of ds, and we'll deal with that here in a minute, times magnitude of r hat, times the sine of the angle between ds and r hat. In this case, that's 90 degrees, right? And then over r squared. So the r is the distance from this point to this point, which is what I'm calling the radius of the semicircle. Now, direction comes from the cross product direction, ds cross r hat. So hopefully you see my video on cross products. Fingers go in the direction of ds, so your fingers should be perfectly parallel to this vector, right hand. Rotate until you can sweep towards this vector. Thumb gives you the direction of the cross product. If you're doing that right, you should be getting something coming basically right at you, and that's in the plus k direction. Cross products are kind of hard to describe on this screen, so hopefully you've seen my other video. I've got a more of a live video that describes how to do cross products. All right, now let's talk about this ds. This ds is a little path length here of a circle. So if we look at this small d theta, ds is coming from the idea of a radian. ds is equal to r times d theta, as long as theta is in radians. So we can go ahead and write this dB equals mu sub I over 4 pi. This ds is equal to r d theta times 1 times sine theta, which is also 1, over r squared. And that's in the k direction. Total magnetic field we get by adding these all up. So we're going to integrate now, and anything that's constant can come out in front. Now mu sub O constant, the current is constant, the 4 pi is constant. And as we move along this path, this r is a constant, so all of that can come out in front. Mu sub O I over 4 pi, let's see, r over r squared, that's going to give us 1r in the bottom. And then we just have the integral of d theta. Theta starts at 0, it goes to pi over 2. So this integral, it's not too tough to show that that's equal to pi over 2. So this thing is going to equal mu sub O I over r, and then we're going to have pi over 2 times 1 over 4 pi, I believe. Let's see, pi over 2, I believe that's 1/8 out of that k direction. Just make sure. Let's see, we're going to have pi over 2 times 1 over 4 pi. Yep, pi's cancel, gives me a 1/8. So the magnetic field expression right here, due to this entire current configuration, is equal to mu sub I over 8r, k direction. So you can see the Biot Savart law isn't always a pain to use. You know, it's just a matter of, in every problem, you draw the ds vector that's always in the direction of the current. You draw the r hat vector that always points towards the point you're interested in, right? So did that here, ds in the direction of the current. R hat points to this spot. Right here, the ds vector points up. R hat points to this spot. Then you evaluate the ds cross r hat. And then you work out the integral. So that's pretty well it for this problem. Hope it helps. Have a great day.